Good day, everyone. This is the video demonstration of our CPN11 final project, the design and simulation of an automated digital queue management system for academic institutions, implemented in both Verilog and VHDL. Academic institutions frequently experience problems with long, disorganized queues in enrollment, records, and cashier offices. Our project addresses this by designing a hardware-based automated digital queue management system, or ADQMS. The system uses finite state machine logic implemented in hardware description languages to automate ticket issuance, service window management, and queue monitoring. Our project has four main objectives. First, to design an FSM-based digital queue system with synthesizable HDL code. Second, to implement the design fully in both Verilog and VHDL, producing to complete and functionally equivalent implementations. Third, to develop separate test benches for each implementation with structured test cases covering all states and transitions. And fourth, to verify correct operation through ISE simulation, waveform analysis, and a comparative analysis of both HDLs. The input, process, output gives a complete functional specification of our system. The 6 inputs are clock, reset, service select, get ticket, call next, and admin reset. These trigger 6 core processes inside the module. First, the FSM state register, a clock sequential process that updates the current state on every rising edge. Second, next state logic, a purely combinational process that evaluates inputs and priority to determine the next state. Third through fifth, the 3 action processes. ISE increments the appropriate queue counter and outputs the ticket number. Serving advances the now serving counter and checks for queue exhaustion, and reset clears all 6 counters. Finally, the output logic drives the ticket ready pulse, queue empty flag, and state out monitor port. The 6 resulting outputs are ticket number, now serving, current service, ticket ready, queue empty, and state out. The top-level RTL schematic of our system as it appears in the Xilinx ISE RTL viewer. At this level, the entire design is represented as a single black box entity named Queue Management System. All 6 input ports are shown on the left side with connecting arrows, and all 6 output ports are shown on the right side. The internal FSM architecture and queue counters are encapsulated inside this module. This top-level view confirms that all ports are correctly declared and connected, with proper bit widths, 7 bits for ticket number and now serving, 2 bits for service select and state out, and 1 bit for the control signals. This is the low-level RTL schematic of our system synthesized in Xilinx ISE targeting the Arctic 7 FPGA. The design utilizes 63 slice registers, 155 slice LUTs, and 27 IOBS for the input and output ports, with a single BUFG driving the global clock, all under 1% of the available Arctic 7 resources, confirming a lightweight and fully synthesizable design. Here we can see the simulation results from Xilinx ISE. Looking at the waveform, we can observe that ticket number increments correctly with each get ticket assertion, from 0 to 1, to 2, and to 3. The now serving signal advances on each call next pulse as expected. The state out signal shows correct FSM transitions, transitioning from 0 for IDLE to 0 for issue and back to idle, and later from 0 to 2 for serving. The queue empty flag correctly goes low when tickets are issued and returns high after all tickets have been served. The ticket ready signal pulses high for exactly 1 clock cycle each time a ticket is issued. Most importantly, the errors register remains at 0 throughout the entire simulation, confirming that all 6 Verilog test cases and all 7 VHDL test cases passed successfully. In conclusion, our group successfully designed and simulated an automated digital queue management system for academic institutions. The FSM-based design with 4 states correctly manages 3 independent service windows. The in-per-output process chart documented all system functions clearly. Both the top-level and low-level RTL views were verified in Xilinx ISE. All 6 Verilog and 7 VHDL test cases passed, with the simulation waveform confirming correct FSM operation. The dual HDL approach strengthened our proficiency in both languages and prepared us for real-world FPGA and ASIC development. Thank you for watching.